This video will include the mixed review questions to help you study for Test 3. Question 1 comes from Unit 1. We're going to simplify this radical that has a fraction. In order to do so, we had to rationalize the denominator. So first, we rewrote this where each the numerator and the denominator was in its own radical. In order to rationalize the denominator, we multiplied by the denominator inside the radical so that we can make that a perfect square. So 2 times 25 gives us 50. 25 times 25 is actually a really large number. That's one of the perfect squares that I don't really know. 25 times 25 is 625. When I see that, I recognize it. Oh yeah, that's a perfect square. But I don't know it right off the top of my head. So we didn't really care so much about seeing that value 625 because we knew once we took the square root, we would end back up with our value. So if you want to, just go ahead and write 25. But we still need to fix and simplify this 50. So let's do our prime factors. When we divide 50 by a prime, I'm going to start with 2. 2 goes into 50 and gives us 25. Divide by another prime, well this time we'll have to use 5. 5 goes into 25 and gives us a 5. And finally we can divide by 5 to give us a 1. We know we're done when we get to that 1. Well, when we see this pair of 5s, that means it gets to go outside the radical. This is really a 25. 5 times 5 is 25. When you take the square root of 25, it gets to come outside the radical. So the 5 is outside because we had a pair of those 5s. And the 2, which does not have a pair, has to be written inside. And then, of course, bring over your 25. We won't be finished until we reduce our fractions. We always need to reduce fractions in math. A 5 can go into itself 1 time, and a 5 can go into 25 5 times. So we can reduce that fraction, and finally our answer is the square root of 2 over 5. If you actually would have noticed from the start, our denominator was already a perfect square. So the square root of 25, you could have gone straight to our final answer if you would have recognized that perfect square. Square root of 25 gives you 5, and of course our numerator would have just stayed the square root of 2. But this process of rationalizing the denominator also works. We would just have to have the added step of reducing. Let's look at question 2. It's also a question from Unit 1. We're going to write an equivalent expression for this radical. So we learned that the index number became our fractional exponent, the denominator, and whatever has an exponent stays as an exponent. So one equivalent way is we kept this exponent up high and we wrote the denominator of a 7. However, that's not the only way this could be represented. What if we just wanted to leave that 4 as the exponent on the a, and we wanted to write this as its own fraction? So again, it comes over just 1 over 7. That would be equivalent to the a raised to the 4/7. It also works that a power to power multiply together. If I multiply 4 times 1/7, we would have gotten 4/7. So it is an equivalent way. You could also even think about, maybe let's take care of the radical, the index number first, and make it a to the 1/7, bringing that around as the denominator of your fractional exponent. And then our exponent that's already there, it will stay as an exponent on the whole problem. Again, this still works that if we multiply those powers together, power to power you multiply, you could get right back to that 4/7. It's just noticing equivalent expressions for a given problem. All of these could equal what we started. Now looking at question 3, we're going to find the sum. So that means we're just going to combine like terms by adding them together. So 9m squared plus an 8m squared. 9 plus 8 gives us 17, and then we have m squared. Keep in mind, when you combine like terms, your answer is that like term. Our next term, because we don't have any other m terms, we'll just bring down the plus 3m. And then finally, our -4, we'll add it with -7. Those are the like terms because they do not have a variable. We call those constants. So -4 plus -7 gives us -11. And that's as far as we can go with that problem. We cannot combine anything else because we have no other like terms. Question number 4. This is from Unit 2. We're going to find the product by multiplying these binomials. So let's first set it up with our 3x. We're going to just distribute with the 4x plus 7. And then that -5, we're going to distribute again with the 4x plus 7. So we're just rewriting it in a way so we can distribute each term to that second parentheses. So 3x times 4x gives us 12x squared. 3x times 7 gives us 21x. And now we'll distribute the -5 to each term. So -5 times 4x is -20x. Being very careful with your sign. Then we'll have -5 times 7 is -35. Be very careful to check your distributive property. I always say watch for your sign, your number, and your variable. So of course our positives, our numbers, and our variables here. Our negatives, our numbers, and our variables there. Always check your work. Our last step, we need to combine our like terms. So here in the center, we should see 21x and a -20x. So bring down the 12x squared. Combine your x terms. 21 take away 20 will just be a 1, which we don't even really need to show that 1. You could show that, but it's just not necessary. And then finally bring down your -35. Question number 5. This comes from Unit 4 when we did graphing. We have this function. It's named g of x. It could really be named anything, f of x, h of x. So this is just the name of the function. This function is in vertex form. So because it's in vertex form, we're able to name the vertex. So the vertex is going to be your hk. So recall vertex form is a times x minus h quantity square plus k. So this was our vertex form. And our vertex is always your hk ordered pair. So the h value, because there's a minus sign and that's how it's supposed to be, our h value, we write down the opposite of what we see. So we're going to write down +23. For the k value, you write down exactly what you see. So if you see a +17, we write down +17. So opposite for the h and exact for the k. Our axis of symmetry number is always going to be the same as your x value of your vertex. So x equals 23. So recall with our parabolas, our U shape, that vertex is where it changed that direction of the U shape. The axis of symmetry is the line that went through the axis of symmetry is the line that went through the parabola, and it always passed right through the vertex. Let's look at max or min. If this vertex would be a max or min. Well, because our a value is negative, so actually let's draw a little sketch of that. Because our a value is negative, it's going to make our parabola open down. And that's because a equals a negative. It opens down. Open, down. So here, by the way, is our vertex that we just named here a minute ago, the 2317. Our axis symmetry line, this is what we just named in part B, that's at x equals 23. So max or min would be this point here, that's the highest point on the graph, so we call it a maximum. Of course, it was the lowest point, it would have been called a minimum. Let's look at question 6. This comes from Unit 5 when we factored. This is a difference of squares. When you have the difference of squares, you take the square root of the first term, square root of the second term, and be careful, you do not need to include the minus sign when you take the square root. It's because it has that minus sign, and these are both perfect squares, that we're able to do this. Of course, the square root of the first term is 2x. The square root of the second term is 5, so we write those terms in our parentheses, 2x and 5, 2x and 5, with a plus and a minus sign. That is the factored form of our difference of squares. Notice the next one is the sum of perfect squares. It's the same two squares that we see from part A, but this one is not factorable. We can actually call it prime. It is prime because it is not factorable. Prime just means the only factors it has is 1 and itself. So we are not able to write it as two sets of parentheses in factored form. Our last one here from Unit 6, we're going to solve, and this is a quadratic. So you actually have different options when solving this quadratic. First, we need to get it set equal to 0. So let's subtract 42 and write them in the correct order. We have our ax squared, our bx, and then finally our c. So ax squared is your x squared term, bx is your x term, and your c is your constant. So when you solve and get it set equal to 0, be sure to write them in the correct order. One of the best ways for students to solve is with a quadratic formula. It's a method that always works, and all you need to do is remember the formula. So x equals negative b plus or minus the square root b squared minus 4ac all over 2a. So that will work for this problem we're going to solve with the quadratic. So our a is 1, b is negative 1, and c is negative 42. So let's plug these in. So negative b, let's go ahead and actually put negative 1 and then your b value, plus or minus the square root b squared. So when you have a negative, make sure you include in parentheses, minus 4 times a times c. Plugging everything in very carefully, watching your signs as you substitute, all over 2a, and our a is a 1. So once you have that set up in your quadratic formula, it's just calculating each part. So negative b, this part we don't really need a calculator for because negative times negative would just be a positive. Plus or minus, let's do our discriminant. So that b squared minus 4ac, negative 1 squared minus 4 times 1 times our c. Being very careful that we typed it in exactly as we need. So that discriminant is 169. It's a good thing to notice that's actually a perfect square, so that's actually going to give us two real solutions that come out as integer values. If this was a negative, we'd have two non-real solutions, and if it came out as a 0, we would have one real solution. But we like it when it's a perfect square because we can take the square root of that value. So take the square root of 169. There we can see. Take the square root of 169, and that gives us 13. So we have 1 plus 13, we'll divide that by 2, and 1 minus 13, we'll divide by 2. So 1 plus 13 gives us 14. When we divide that by 2, we get a 7. 1 minus 13 is negative 12. When we divide that by 2, we get negative 6. So our solutions in set notation, when we order them least to greatest, would be negative 6 and 7. Although this is a method that always works, it's not actually my favorite method. So in order to solve this quadratic, I'm actually going to show it by factoring. So let's start back where we were, where it was set equal to 0. We have x squared minus x minus 42 equals 0. When it is factorable, I try to factor it. It's a faster method and one that I make fewer mistakes on. So because this is a trinomial, I'm going to do the product sum method. So a times our c, we want the factors of negative 42 is our 1 times negative 42 is your product number, and then your sum number is your b. So I need to come up with the factors of negative 42, meaning I need one positive and one negative, that are going to give me a sum of negative 1. So if you think through the list of factors of 42, you will come up and find that you'll need a positive 6 and a negative 7. So let's rewrite this with those two numbers. Positive 6x minus 7x minus 42. And typically I would not have put this negative here, but I want to remind you about when that first term is negative. If I could have, I would have normally rearranged these so I don't have to factor out a negative. So let's go ahead and see this first group. What they have in common is an x. The leftovers are x plus 6. When I factor out an x is left over for the first term. And when I factor out an x, a 6 is left over for the second term. So let's look at the next group. When I factor out, I have to do a negative because that first term's negative. When I factor out what they have in common, they have a 7. So we'll be factoring a negative 7 as our greatest common factor. Well, this becomes an x because when I factor out a negative 7, that's all that is left. When I factor out a negative 7 from the negative 42, know that it needs to become positive because factoring out that negative leaves us with a positive. And 7 divides into 42 and gives us a 6. So noticing our leftover parentheses do match. So that's going to become one set of the parentheses, x plus 6, and the other one is x minus 7. So we've done that work in solving, we've done that work in factoring, but we actually need to solve. So let's set each factor, x plus 6 equal to 0 and x minus 7 equal to 0. Once we set each factor equal to 0, we can solve for x. So x equals negative 6 and x equals 7. So again, we find the same solutions just with a different method for our quadratic. Of course, use whatever you prefer when solving quadratics. You could also do completing the square. However, with this quadratic, it may not be the best method because our b is an odd number, which it could work, but it's not pleasant. So either choose quadratic formula or by factoring when solving quadratics.